So this is the lecture about filtering, and we are going to first talk about images, what kind of images we have. So the simplest kind of image is a binary image, which is shown in the first one on the left, and then grayscale image, and then we have the color image. So binary image has only two levels, black and white. The grayscale image has 0 to 255, and then the color image has 3 colors. So here's an example of a binary image. And image, as we talked about, it's a matrix of numbers. We have rows and we have columns. So row 1 to row Q, and column 1 to column P. And so we will have these numbers in each element of this array. If it is 0, then it will be black. If it is 1, it's white. It's a binary image. Then we have a gray level image, so exactly same thing, but now we will have numbers from 0 to 255. So 0 is black, 250 has white, and we have any number between them which will be gray. And that's what's shown on the right side here, that this is completely black and this is white, and you have whole shades of gray. Then we can see this also as a color channel. Like we can see this gray level image as a red channel. It looks like that. So the color images actually have 3 channels: red, green, and blue. So therefore we have 3 arrays: one for red, one for green, and one for blue. And each of them again have number from 0 to 55. So now one important property of an image, or the feature of an image, is called histogram, which give you a distribution. What are these different gray levels we have in the image and how many times that occur. So histogram gives a distribution. So as you see here, we have these different gray levels from 0 to 55. And here we have the percentage of the pixels in this image we have. Suppose we have a lot of pixels around this gray level, which is very high, but very few pixels we have these gray levels. So that gives you overall distribution, and that's a very important property of an image, and we are going to use that. It's called a histogram. Okay, so you just count the number of pixel gray level, say 0, number of pixel gray level 1, 2, 3, you go all the way to 255, and that gives you histogram. So now important thing we have to notice that when we have these images, they may contain noise, and noise can be due to lighting variations and camera electronics and surface reflectance and lens and all those things. Even though the quality of images have been improving over the years, when I was a graduate student, image quality would be very bad. Now we have a really good image, but still we have to consider the noise factor. So what we are going to do is look at what we mean by a noise and try to undo that. We want to remove noise, or we want to filter out a noise. So let's say we have an image I, and since I say it's a matrix of numbers, so we will have 2 indices, x and y. Okay, so x will tell you what row it is, and y will tell you what column it is. So the true pixel value may be ixy, it may be something 30 or something, but what we are going to observe will be some noise in it, and to simplify we will have this additive noise model. So actual image value ixy, there will be some noise added randomly, and what we will observe will be I hat xy. Okay, so this may be the actual image, but due to noise we may get something like that, which is not that good. Okay, so now the main question is what is the model of noise, because noise has to have a distribution. So we don't know exactly every pixel what's a noise. If we know that, then it's not noise. The reason we call it noise because we don't know much about it. Okay, but we may know the distribution. So as you know, there are many distributions you might have read in the probability or statistic course. The simple distribution is uniform distribution, that all the possible values have equal probability. If I flip a coin, head and tail has half and half. No, that's a uniform distribution. If I roll a die, it is 9 or 6 possible outcomes. So every possible outcome is 1 upon 6. This is a uniform distribution. But there are distribution which is the Gaussian distribution or a bell curve distribution, normal distribution, and so on. You must have heard about that. That is the Gaussian distribution, which is shown here. Now this has a 0 mean and standard deviation is sigma. So many times the noise can be modeled actually by a Gaussian distribution, which means this is a Gaussian, it is around 0 mean. So most of the time there won't be noise actually. And probability that it has little bit noise around here will be very high, but probability that it has a very large noise will be very low, or very small noise will be low. So that's why Gaussian distribution. So, so given that, now we want to look into what we can do with images. So one important operation in computer vision, which we are going to do with images, is we will find the derivatives of images. We are going to differentiate images. You know, you have heard in calculus, you have learned, you're given a function, you can differentiate it, you can find first derivative, second derivative, and so on. Now here you will see what are the application of these derivative. What does derivative mean and how can you use it, and which is pretty interesting. So you'll see really application. So now if you look at the definition of derivative, it's a very intuitive, say rate of change. Something, you know, you look at like a speed is a rate of change of a distance, acceleration is rate of change of speed. So then other concept is average. You know, it's a mean. You take the bunch of values, divide by number of items you have, that get the average. So derivative in calculus, you heard that if you have function f, you want, if it's a function of x, then you want to differentiate with respect to x. This is a definition. You take the value of f at x and take the value of f at close to x, maybe x minus delta x, and find a difference and divide by delta x. That give you the rate of change. This give you the change, and this give you how much is the distance we are changing. Okay, that's a definition from calculus. And we are going to represent this f prime x or fx, you know, because it's a function of two variables, so you know we will have partial derivative. This is the derivative with respect to x. And this particular thing is only one function of one variable, so you know it's implied that we are computing derivative with respect to x. So now speed is derivative of distance with respect to time. The acceleration is derivative of velocity or speed with respect to time. And so we have examples. You know, if you have analytical expression like this, y is equal to x squared plus x4, so then you can differentiate with respect to x, so it will become 2x and plus 4x cubed. You know, you know that. And if you have the exponential like sine x plus e to the power minus x will be derivative of sine x is cos x, and derivative of e minus x is e minus x with minus, and things like that. Now what we will have to deal with computer vision, that we don't have functions like in calculus you learn. We have actually data, we have images. So we have to come up with the approximation of derivative in the discrete domain, because the images are discrete, which means we have number, row number 1, row number 2, 3, column number 1, 2, 3. We don't have row number 1.2 or 9.3. No, that's what the computers are about. Everything is discrete. So therefore we'll take this definition and then we will approximate and say, well, what is the smallest delta x we can choose? You know, smallest delta x is 1, right? I mean, if you do smaller than that, it'll become 0, and that doesn't make sense. So we are going to use 1, then it will become f of x minus f of x minus 1 divided by 1, and that is the first derivative with respect to x. And that is pretty simple. So what we are saying, if you want to differentiate a one-dimensional function, we take the value at x, we subtract it from previous, and we find a derivative. And it's very simple. Okay? So therefore now we took the value previously, and that's why it's called backward difference. okay? But we could have taken a value after that. So that will be x plus 1, and that will call forward difference, okay? And then we can do actually center difference. We can take the one on the left, one on the right, and find a difference. So there are different approximation of what's the best way to find derivative, but you got an idea. So now let's say we have a row of an image which looks like that, because we want to explain this in one dimension, then we'll extend to two dimension. So the one pixel is 10, then 15, 10, 10, 25, 20, 20. And so we want to find a derivative of this. We just describe that we can find the backward difference. So suppose we cannot find derivative here because we don't have a one before that, so the border. So we'll just put a 0 here. Okay. So here this is the first place we can find derivative. So 15 minus 10 is 5. 10 minus 15 is minus 5, 10 minus 10 is 0, 25 minus 10 is 15, and so on. So this will be the first derivative of this. It's pretty simple. Now we can find the second derivative by just finding the first derivative of first derivative. Okay, so this again will be 0, so 5 minus 0 is 5, minus 5 is minus 10, 0 minus minus 5 is 5, and so on. So this way we can find these derivatives as many times as we want. So now there's an interesting notion of what we call a mask. So essentially this is a backward difference mask. So what we are doing, we take a mask, we center it here where we want to compute, we multiply 1 by 15, multiply minus 1 by 10, and add it up. Okay, so then we want to put it here, multiply 1 by 10 minus 1 by 15, add it up, we get the result here. Then here again center it here, so it will be 1 multiplied by 10, 10 multiplied by minus 1, sum it up, and like that. So that's called application of this mask, and we are going to extend that to more concepts. So that's for forward difference, which is different, that minus 1, 1, and then the center difference, we are going to look at the 1, 0, minus 1, because the central pixel we are going to compute derivative. We are not going to use that as I showed you before, but we look at the one on the left side and one on the right side, we find the difference. So it's a pretty interesting way to find the derivative of a one-dimensional function. So now images are two-dimensional because, as we said, we have rows and we have columns. Okay, so therefore our function now is of two dimension, x and y. Okay, so therefore we will have two derivatives. We'll have two partial derivatives. One will be derivative of f with respect to x, and other will be derivative of f with respect to y. And so it will be fx and fy, and this will be a vector because it has two numbers. If it's just one number, it's called scalar. There are two numbers, it's called vector. So which means that it will have magnitude. To find the magnitude of vector, we take the first element, square it, second element, square it, and square root, and the direction, which is the tangent inverse of fy upon fx. So this vector will have the magnitude and the direction, and that's a derivative of an image. Because image is a two-dimension, we will have two numbers. Okay, so now as we did before for the one dimension, we can come up with the masks for the two dimension, and we can compute the derivative of an image, and that if you extend the idea which we were talking about, that if we want to find the derivative in x direction, and suppose we want to use the center difference, then actually this will be the mask we are going to apply, 1, 0, minus 1. But now what happened, in addition to finding the change, we want to kind of do the average, and average is one way to kind of get rid of noise. Okay, so therefore what we are going to do is not only find this difference at this row where we want to find, but we are going to find a difference, one above that row and one below that row. So we'll have three differences, and we are going to add them up and divide by 3, and we'll get a better approximation of derivative. So that's the idea, that we have this 3 by 3 mask for the first derivative, of an image with respect to x. So, and similarly we can find the first derivative with respect to y. Now we will have the difference in y direction. Again, we can have just used this one, but we are going to use these two, one on the left, one on the right, to get a better approximation. If there's a noise, the noise may be in the central pixel or left pixel, but that noise will be now distributed. It will average out, and that's what we want. Okay, so let's take an image like this. We have an image, now it's rows and columns, we have 5 rows, 5 columns, and we want to find the first derivative of this with respect to x. So we will basically get the first derivative, which is like this, and say we want to find the first derivative at this pixel. Okay, so we'll take our mask here and multiply this corresponding element, -1 with 10, -1 with 10, -1 with 10, and 0 with this, and then 1 with 20, 1 with 20, and then sum it up. So as you see, this will give us a 10, this will give us 10, this will give us 10, add them up 30, divide by 3, it will become 10. So that's what we have here. And we will shift, now you want to find out here, again, here we will center and then multiply this corresponding element, and we are going to get what the value 10, and so on. As you see here also, the border pixels we put zeros. We cannot apply this mask because we don't have the left side and the top side and so on. So that's the process, that we have applied a mask to compute the derivative of this image with respect to x, and everything is intuitive, it makes sense. Okay, so now we can do, let's say, apply with respect to y. We want to find the derivative with respect to y. Okay, so as you saw there, that this was the mask for y. We are going to find the difference in the column wise. Now if you see here that, if I subtract, suppose first place I'm going to apply it here. So I subtract 10 minus 10, 10 minus 10, 20 minus 20, it's all 0. Yes? So there's nothing changing in y direction in this, they are the same. So therefore I will get zeros, and you can verify that. Okay? So that is the derivative with respect to y. Just apply that mask. It's pretty simple. So now there's this notion called correlation, and that essentially does that. So we have f, which is say our image, and h is its mask, and this, when we are applying this, as you saw, we are applying every row and every column in the 3 by 3. So when you go through each row, then it's one summation, one loop, and when you given a row, you go through every column, another loop. So that's why we have these two summations. So this is a process that we take the values of f and take the corresponding values of this mask or kernel and multiply, and we do this for, if it is 3 by 3, we do this for 9 pixels. 3 rows, 3 columns. If it is 5 by 5, we do for 25 pixels, and so on. So that is the sign we are going to use for correlation. Okay? So now, so f is image and f is a kernel or a mask. So let's say our image is again very simple, it's just 3 by 3. So we have these value f1 to f9, and then we want to do correlation, and this is our mask, and then we are going to essentially expand this summation, and the process, as I told you, we multiply this with that, this with that, this with that, and so on. That's the convolution. So it gives you an equation, the process which I explained to you intuitively what we are doing. Okay, and in your program this is 2 loops, go through each row, there are 3 rows, and given a row you go through each column. Okay? Yes?
What is correlation measuring?
It measures how similar two things are, because you're multiplying. So if they are similar, the sum will be high. They are not similar, and we'll talk more about that. So now there's another operation which is convolution. They are very similar and little difference. And the only difference is that here we are going to flip these. As you saw there, we had the I plus k and j plus l. Here we have I minus k and j minus l. Okay? But it's again two summations, two loops, and we have an image, and then we have a mask, our kernel. So then if this is our kernel or a mask, then we are going to flip that, the x flip. So we are going to take this and flip it like that. So after the x flip, it will look like that. As you see, the central row will remain there, but now we are going to flip. The bottom row will become top, and top will become bottom. Yes? See, compare this with that. So then we are going to flip, after the flipping, in the y. So now we are going to flip like columns. So like that. So that will become our mask we are going to apply, because this is the convolution by definition. We are going to flip that. And then we will just apply to to the, as we are doing, the f, and then we'll get like that. Okay? So now this is different than the correlation, because we did not flip there. Here we are flipping, so these numbers are changed. But you will realize that if this to start with was symmetric, you know, like a Gaussian, then flipping will not make a difference. Okay? Because in the Gaussian, as you know, that this value and this value is same. This value and this value is same. So when flipping these, it will not make a difference. So in that cases, the convolution and correlation actually is same. There's no difference. But if they are not symmetric, this mask is not symmetric, then they are different. So that's the idea. Okay? So the convolution and correlation. And so we get back to now mean. Mean will be very useful. And so mean is, you know, everybody knows what the mean is. You know, you take a bunch of numbers, you add them up and count how many numbers you have, you divide by that. That's mean. It's pretty simple. Now there is something called weighted mean, which means you apply some weight to each item and then again sum them up and then divide by that. So that these weights are W1, W2 and so on, and then you divide by that. So now when we apply a Gaussian to the image, so actually we are doing kind of weighted mean. Okay? So previously we were just adding up and divide by 3. But here we are going to apply the values according to where these pixels are. If they are close to the center, will be a high value. So away from it, the value will reduce, as you see here. So again, this is the expression for Gaussian. And we are going to use this again and again, and you know, you should feel comfortable. It's a very simple thing. So this is a mean is 0 here, and the standard deviation is sigma. And it's a one-dimensional Gaussian. And this is a two-dimensional Gaussian, which is same thing in x and y. And this is written like that. E to the power minus x squared plus y squared upon 2 sigma squared. Okay, 0 mean, again, the, you know, same standard deviation both. So now we can take different values of x in this and then substitute in this equation using your calculator. Then you will get the value of g of x. So suppose if I put x is equal to 0, what I'm going to get here?
1.
Great. If I put x is equal to 1 and sigma is 1, I'm going to get 0.6. X is equal to 2, I'm going to get 0.13. It's equal to 3, 0.011. And since this is symmetric, on the left side will be the same. -1, -2, -3. So that these are the mask value of a Gaussian filter in one dimension. I have an equation for that, and I can generate this mask also. And I can do the same thing as I was doing for the difference, -1, 1 or whatever. Okay, so this is fun. So this is the Gaussian filter. Then, yeah, sigma is 1. So now the interesting thing about Gaussian is, this is, you know, has different names. Standard, yes, please.
What does sigma indicate on
Sigma is standard deviation. So whenever you have the distribution, any distribution has a mean and standard deviation. Okay, mean say what is the average. Standard deviation is how it's changing. Now if sigma is 1, it looks like that. When I have sigma is equal to 2, it will flatten up. Sigma is 3 equal to even more. That's the property of the distribution. Okay, so please say, because I'm kind of, it's a big class, so sometimes I don't see if somebody has a question, so please feel free to stop me if you have any question. Okay, so now the Gaussian has lots of good properties. So Gaussian is called Gaussian distribution, normal distribution, bell curve, and there are lots of names for that. The interesting thing is that so it's after very famous mathematician, physicist called Gauss, and it was German scientist. He was very prodigy from the beginning. He used to be in the elementary school. So the teacher gave a homework, give a problem on the board, say, well, sum up numbers from 1 to 10 and give me the answer. Then this guy quickly came and gave answer. Then other people are still working on that problem. Then this guy was restless. Then he said, well, okay, sum up from 1 to 30. Then he took exactly the same time and said, so that's the answer. Then the teacher got really upset. Said, sum up to 1 to 1,000. Then it's exactly same time. So he came up with, as you guys know, that it's n plus 1 upon 2. If you have numbers from 1 to n, their sum is n plus 1 upon 2. So you've discovered this formula because you can take 1 to 10 is 11, 2 to 9 is 11, 3 to 8 is 11. You make pairs and you have half of them and so on. So the guy is great and did lots of contribution and so on. So this function is named after him, and probably he came up with first time. So the most of the natural phenomena can be modeled by bell curve or Gaussian distribution. So if I take the height of people in this class, it will follow a Gaussian distribution. There will be average. Most of people will be average. Be some very tall, some very short, and so on. If you look at IQ, if you look at ages, if you look at all these things, or Gaussian distribution, rain, fall, and all those things. So now for us in computer vision, these are mathematics. This is a very nice smooth function, which means the function is smooth that you can differentiate as many times as you want. So Gaussian you can differentiate infinite number of times. So that's why it is a good function and symmetric and all those things. There's another thing is what is called, we can look at the functions or signals in the frequency domain. It's called Fourier transform. Some of you may know. So if you take a Gaussian function, find this Fourier transform, it's again in Gaussian. It doesn't change. It looks the same. And now, as you learn from here, Gaussian, the convolution idea. So if you take a Gaussian convolve with itself, so where the mask is Gaussian and actually image is Gaussian, then you will get another Gaussian. So which is pretty interesting with a bigger sigma value. So and for us the interesting thing is that in the human retina brain there are these cells, neurons, whose response is basically Gaussian. And so they take whatever we see, they apply Gaussian filters to those pixels, and that there's a big research in neuroscience where they have been talking about these different cells. And we have talked about age detector, which is based on Gaussian. So it's a pretty interesting thing. We can keep talking about Gaussian. So it's good to know that. So again, going back to filtering, so we are going to modify the pixels in the image which we get. So let's say this is a 3x3 neighborhood in the image, and we are going to talk about filtering. Means we are going to apply something to this 3x3 and modify the pixels. Suppose this 11 will be replaced by 5.7, and based on the neighboring pixel. So that's what the filtering does, and that's what as you saw there. So let's say this is our image, and this is a kernel. Okay. So again, as we say, we are going to multiply corresponding pixels, 1 with 1, 1 with 2, 1 with 4, and all this, add it up, and we'll get 5 value here. Now this 10 is replaced by 5, and we are going to do this for all the pixels. So that's the filtering idea. So filtering, the idea is that, well, what is the kernel? What is a mask? And that's what we are going to talk about that. So let's say here, there's a simple filtering example where the mask is, we are going to look at 3 by 3, and we are going to just replace it with cell. Actually, this is doing nothing, but this is just example that look at every pixel, look at 3 by 3, look at its values. We are going to do something as we did here and replace by that, but here this is also a kernel, but which means do nothing. Okay. So then this is another example of mask. Somehow we are going to replace with the one on the right, this pixel. So the 0, 0, and there's 1. So this is what you're going to get with that. And this is like averaging. So take the values, 9 values, sum it up, divide by 9, and you get something like that. And we are going to do this for every pixels except the border pixels. That means that we apply this filter, this mask to the image, and this is the filter image, and this is a kernel or a mask. Okay. So we can have lots of examples. Now this is a 5 by 5 mask. So we have 25 values. Again, we are going to sum up these 25 values, divide by 25, and replace the number. And go to the next one, next one, next one, and so on. We'll have these loops. So in the one dimension case, here is your one dimension case, and this is the kind of your mask applied to this, and you get filter like this. This can be original, this can be a mask, and you get like that. So you get an idea. Now we can do the filtering with Gaussian. So we will have the Gaussian mask like that. As I showed you, it looks like a like a hat, bell, and then it will look like that after filtering. So then the question is that the Gaussian mask, what it's doing, it's doing the weighted averaging. Because as you saw, these weights we had, the central pixel is 1, the next one 0.6, next one 0.13, and so on. So the weight is going down according to this curve. When you do the just averaging, the weight is same for everything. So that's why it's called weighted averaging. So which means you want to make the central pixel more important than the other pixel. As you go away from the central pixel, the weight reduces, which makes sense. Okay. So now this is the Gaussian smoothing, and this is averaging. So as you see, Gaussian smoothing is much more interesting, better. The just smoothing is kind of blurred because just doing the averaging. So that's the idea. So now, one is that we have a Gaussian filter. So you need to be very clear about, because some people get confused. So we talk about filter, talk about kernel, talk about correlation, convolution. There's a whole concept there. And in brief, the idea is that we will have some mask, and we want to apply that mask to the image and get the resultant image, filtered image. And these can be averaging, can be Gaussian, can be derivative, and all possible things. So then there is notion of the Gaussian also. In that case, the Gaussian was a filter, which will remove noise. Now Gaussian is also a distribution, as we talked about, distribution. So whenever you want to model a noise, you can model noise by a distribution. And as I showed you examples before, that we can add Gaussian noise to the image, and this may look like this. we change the value of the pixel based on randomly by generating a Gaussian random variable, and whatever value we get, we add that to the actual pixel, and then the pixel modified like that, and this looks the added Gaussian noise to the image. Now, since it has a noise, so we want to remove the noise, and now removing noise, we do the smoothing. We can do two ways. One is we just do averaging, and this is what averaging is. Or we can do Gaussian smoothing, and this is what we get. So as you see, the Gaussian is so important here that it's playing both roles. The distribution of noise and also as a filter. So that makes it interesting. Okay, so now there are these MATLAB functions which you will be using to do these operations. And as we say, we will have this MATLAB session. I'm trying to get a room, but somehow there's a very lengthy process to schedule this thing. So I'm going to send you email once I get the room. So, but I'll give you a preview of these functions which you can start looking into. So one is the convolution function, and it is just a 1D convolution. Okay, so A and B are vectors, and you can convolve A and B and get you the result C. Okay, then we have similar thing for 2 dimensions. That's what you will be using in the images. So convolve 2, and here instead of A, B being vectors, there will be a matrices. There will be the mask and the image. Okay, and then we have a filter 2, so it can be any filter, digital filter. So again here we will have that it will filter the data in X with this filter, and you can define that what is that filter P. The result is computed in Y. So this is the input matrix. This is your filter, and the result is here, and it uses the correlation of the same size X. Now, so you will do this most of the time. This will do for you, and also as we talked about, there's a difference between convolution and correlation. So that's why it's talking about would be 180 degrees rotation. So then we have another function called gradient, which will approximate the gradient as we talk about the first derivative in X, first derivative Y. So this fx, fy. So if you take an image f, say gradient of f, which will give you fx matrix, fy matrix. Fx will have first derivative of the image, fy will have first derivative of the first derivative image with x and first derivative image with y. Mean, of course, it will do the average mean value, and you can do for vector, you can do for matrices, and so on. So then I think the interesting function is called the spatial, and it is you can create different filters using this, and so it will be the f spatial. You can put a type, what type of the filter you want, and generate that in H. And there are possible types. It can do averaging, and you have to specify how big the filter should be. And then if you put Gaussian, it will actually generate a Gaussian filter. And you can do Laplacian, we're going to talk about that, which will generate Laplacian operator. Laplacian is essentially the second derivative of x plus second derivative of y. That's called Laplacian. Okay? Then we have a Laplacian Gaussian, which is an edge detector. We're going to talk about that. It can generate that also. And then we have this private or a horizontal edge detector. It can generate that. Sawbale edge detector. And so example is shown here, that if I say H is f spatial Gaussian 7,1, so it's going to generate a Gaussian filter with sigma 1 or variance 1, and the size of filter is 7 by 7. Okay? And the reason is 7 by 7 because, as you know, that if you have a Gaussian distribution, after 3 sigma, if the sigma is 1, okay, then after 3 sigma, or after 3, then the value of Gaussian distribution will be almost 0. 99% will be gone. Yes? That's what the whole thing is. So, which means that in order to cover the whole Gaussian, you need to have at least 3 on this side, 3 on this side, and 1 in the center. So at least you tend to have 7 by 7 mask. If you use, say, 3 by 3, then you won't get a full Gaussian. You know, because you have 1 here, 1 here. At 1, the Gaussian is 0.6, 0.6, but you are not getting the big thing. So that's also important, that depending on the sigma, you will have to use a bigger size of a mask. And we are going to discuss that thing. That's important thing in computer vision is called scale. What is a scale? And if you don't know the scale, then you will have to use lots of scales. And that's called a scale space. And we're going to talk about that. But this function will do a lot for you, these kind of functions. And the idea is that MATLAB, once you understand these concepts, then your programming will be easy. You can just use that as compared to write your C program, where you'll have these 2 loops. You know, you'll have 2 loops for the image going through, 2 loops for the element mass going through, so it will become, you know, more lengthy. But you do need to understand conceptually, because that's what we will test in the homework and the exam. But programming using MATLAB, I think it'll be easier for you guys. Yeah, so so that's kind of ends this first lecture. Now I can open the floor for questions. You know, you have any questions? Anything which is not clear? Just feel free. I can explain in detail something.
How do you know
Yeah.
like an image needs a filter?
Yeah, so that's a good question. So see, the better way to ask this, well, how do you know how much filtering it needs? No, because some images may be very noisy, and you need a lot of smoothing, and some may not need that much. So that's again the idea of sigma for Gaussian is that if you use a larger sigma, then it can smooth it out a lot, because you're looking at a bigger neighborhood. So therefore, if you don't know how much smoothing you need to apply several smoothing, sigma 1, sigma 2, sigma 3, and so on, and then getting those images and make sense of that. So we don't know, you know, a priori, you know, a computer cannot determine what sigma to use. So that's the, I think, important problem in vision. But the capturing this information at different scale, different neighborhoods, I think is more interesting, and we're going to get into that in more detail, which is of the scale issue. See, it's also not even, you know, it can be, doesn't have to be related to the noise. You know, like if you take a picture, this monitor is at certain distance, it'll appear this much. If I take a picture very far, it'll appear small. That's again a monitor. So there are these different scales. Now how do I deal with that, you know, because computer doesn't know where the picture was taken. So there are ways to deal with these scale space, and we are going to go in detail. In particular, you know, we are going to talk about the shift descriptor or shift detector, and there's a whole idea of the scale, and you're going to implement that. And so briefly, that we will have to use multiple scales and automatically determine what's the right scale depending on the response. But we cannot use just one scale because we don't know. Okay, that's a good question. More question, yeah.
What is the point convolution? What does convolution do exactly?
As you saw that we can use the convolution to find the derivative of an image. You can differentiate, and we're going to talk about in order to find edges in an image, we have to differentiate an image. Because see, the edges are where the change is occurring. So derivative find the change. So in order to find the derivative, we'll do the convolution or apply a mask. In order to do smoothing, to remove noise, we'll do the convolution. So these are the basic operation we are going to apply to the image to get something meaningful from an image. As you saw, image has many rows, many columns, there are numbers. Now a computer, look at number, doesn't know what is there, So we are going to do the abstraction of an image, that we are going to focus on the important features of an image. For example, if the image is of this chair, then chair can be described, say, well, there are legs, there's a back, there's a seat, there's this thing you can put your book on. And so from that, how do you get started? So I'll say, let's find the boundaries of these, the legs, the seat, and so on. Then we have a surface. This is where you sit in. This is your back. So that's the process we are going to go through, because then we can focus on the symbolic information, which is a line, a leg, and the back, and that's meaningful for our humans. And in order to do that, we have to do the edge detection, we have to find derivatives, we have to look at all these things. Because if you look at, we're getting into the next lecture, that when you have a constant numbers, then there's nothing, it does not provide you any information. And when there's a change, that's going to provide you information. That's what we are going to focus on. Okay, more questions? Yes?
I'm just curious about the noise reduction. Because that came up a couple times in the lecture. It looked like near the end there you had a slide that was like, in order to do noise reduction, basically we'll do like a Gaussian or a low pass filter or something.
Yeah.
Are there better ways to do that, or does that work well in practice? Because if you have an image with a lot of detail and you put a filter on it, then you kind of in some cases you can lose a lot of it.
Yeah. That's right. That's a good question. Yeah. So see, the filtering is still a research area that people are working on. That first is, what is the right filter, and how much do you filter, as I told you before. So as you are saying, that if they have image, there's a lot of texture, lots of things, little things, and if you smooth it too much, then you lose the details, And there may be some other images, where not many details, and there's some random noise and so on. Maybe you should smooth that. So this is one filter which somehow works pretty well most of the cases, most of the things we are going to do, because it is kind of averaging, it's doing the averaging, and the intuition is that, well, if there's a noise at a pixel, then we have to look at its neighbors, and hopefully neighbors doesn't have noise, because see, the noise is random. The probability that this pixel has a noise and next pixel has noise is very low, because it's independent, it's random. Yes? So therefore, the filtering idea is that we are going to rely on the neighboring pixels to help us. And then the idea is that, well, how much weight we apply to neighboring pixel. If you do averaging, then we are saying equally likely. Each neighbor is equal likely. It has important, even though the pixel is 5 pixels away from it. For Gaussian, what we are doing is we are saying that if the pixel is very close to the current pixel, then we apply more weight. So that's the notion of Gaussian. And then there are these studies that actually these filters, Gaussian filters, we actually have in the brain, in the retina. That's what we are doing, human beings. And that was one of the motivation that people started looking at the Gaussian and Laplacian Gaussian and so on. Okay. More question? Yeah.
Is the Gaussian the only thing that the eye has?
It is. I mean, that's a basic, basic thing, and there are some variations of that, and there are lots of things. But again, that's a whole interesting area. There's a lot of research, and people. The guy who discovered, the couple guy from Harvard University, Hubel and Wiesel, they came up with this notion long time ago. But there are some other cells which are actually sensitive to the motion, So if something is moving, they will fire, And there are some other cells which will look at the orientation of something oriented like this, they will fire as compared to this one, and so on. So there's a whole lot going on in that. But somehow Gaussian is a very simple, easy to understand, and it works, and that's why people are stuck with that. There was another question. Yeah, here. Yeah, go ahead. It's you. You can go ahead. Yeah.
C is the convolution of matrix A and B. How can I know the size of C?
The C, you mean the kernel?
C, matrix C, is the result of the convolution of matrix A and matrix B.
Yeah, so see, you will have matrix A, which is like in your image, and then you will have the kernel, the mask, which will be normally smaller than your original image. And the result you will get will be same as the matrix A. Okay, so it will be the same matrix. Of course, you will have zeros on the border because you cannot compute. And mask you will apply, you will fill in all the zeros for the rest of the elements. So maybe I'm not following. What do you mean by, you will tell what is the size of a...
I am doing the convolution of
Yeah.
matrix A of
3 by 3.
3 by 3,
Yes.
and matrix B 3 by 3, and
Yes.
I get one matrix by 5 by 5.
Uh-huh.
So I don't know how the size is.
So your mask is 3 by 3,
Yes.
and then image is 5 by 5. Yeah, MATLAB will take care of that. You just have to specify, because see, once you declare your image, MATLAB knows what is the size of how many rows, how many columns it has. So it will take care of it, and you can find even by size command, it will tell you how many columns, how many rows you have, and you will know more about it in the tutorial on MATLAB. Okay. Any more questions? More questions you ask, it will slow me down. That I will not cover more material, and if there are no questions, then I'll go to the next lecture. So we are going to start the next lecture, which is on the edge detection, and that will get into the discussion we were having before. So given in this image, we want to find the edges, and as we would know, what the edges are, the boundaries of this object. Now these are the boundaries, physical boundary. Then there are edges between these labels also. There's a label of a beer bottle and so on. There's edge here. There may be edge due to noise and so on. So that's what we want. And there's another example. Again, we want the edges like that. Okay. So now, what is application of edge? As I told you, that's a basic building block when we want to analyze images. We want to reduce the information because there's a lot of pixels, and most of pixels are not relevant, not informative, and we can find those edges. Suppose we are looking at this picture. Maybe the face is relevant, and the eyes and nose within the face, and so on. We can find the relevant information. So that's what edge detection is going to help you for that. So now edges, as we talked about, that edges are places where something changes. There's a discontinuity. So here, suppose see in this one there's an edge. This is an edge because this is completely white, this is red, so the big change. Again, there's an edge here. If you look at here, there's an edge here, this object, and then the object is resting on. And then even there's an edge due to, in the same object, due to different texture, different gray level. So these are the edges. So wherever there's a change, that's an edge. So there are different models of edges in one dimension. So the simplest model is step edge. See, the intensity value is constant, then all of a sudden becomes something else. So this is an edge. Okay. Now other possible models are like at this edge. So this is not instantaneous like a step edge here, but it goes slowly, changes slowly edge. It's called a ramp edge. There can be spike, very thin edge, or that can be roof edge, change then go down like that. So there are different models of edges. So we are going to, in order to detect edges, we are going to look at the derivatives of the image, and that's what we have been talking about. So again, this is a definition of the derivative. Since it's a two-dimensional function, we are going to look at x derivative, y derivative, and we are going to convolve the image with the derivative filters. We talked about backward filter, forward difference, and so on. So the derivative is defined like that, and this is kind of repeat, and x derivative, y derivative, and then we will approximate by delta x will be 1, and then we'll have a kernel as we have mentioned before. So now if you take an image like this, if you find the x derivative, it will look like that. Now here is simplified kernel. As we say, we just look at 2 pixels, backward, forward, backward, but better way will be look at 3 by 3 to average out. So this is just an example. So this is a derivative is changing in x direction, what's a change, and this is in y direction, what's a change. So then the noise affect the images and derivative and pixels that look different from its neighbors, and if you have more noise, then it will have strong response. And so what we do, as I said earlier, that we are going to leverage the information in the neighbors to deal with the noise, because the main point is that we have some basics. We want to say the neighboring pixel look similar. So if the pixel randomly is some noise, very high value, we know this is not correct. So we want to reduce it based on the neighboring value, and that's what the filtering does. We want to average out. Also, if you have an edge, and then the pixels around the edge should be similar, and also we need to smooth the image to remove noise and things like that. So this gives you an example of an image. We can artificially add different noise. As you see, it's becoming noisy, and this is another image, like that, and we are adding Gaussian noise with zero mean with increasing sigma. So now getting back to smoothing, that we want to smooth the image to remove noise so that the pixels look similar to its neighbors, and smoothing will suppress the noise. So here is example again, that we can apply a Gaussian filter to this, and this looks better because we have suppressed the noise. And then as we talk about, the question is what should be the standard deviation, what should be the these Gaussian standard deviation. If it increases, then image is blurred, and then of course if the noise is more, then we want to apply higher value of sigma value. Okay, so here are some more example. So here we are showing the different added noise, and then the result of applying the smoothing. Okay, So this example is no smoothing, and then we have these different versions of that where we are showing that in order to deal with more noise, we have to do more smoothing. Okay, and so edge detector, the simplest edge detectors are called Prewitt edge detector and Sobel edge detector. These are pretty old. These are names of the authors who came up with these edge detector, and they are very intuitive. So the better one is called Laplacian Gaussian, and that's why I say the Gaussian has been very popular. And this was developed by Moore and Hildreth, and we are going to talk about in detail. And then there's another good, even better than Laplacian Gaussian, is called Caney edge detector, and that's probably the ultimate. That's the best edge detector. So let's look at Prewitt and Sobel edge detectors, and these essentially just compute the derivative in x and y direction with some smoothing, and find the magnitude, and then apply threshold the magnitude. So if the derivative magnitude is high, then that's h, otherwise not h. That's it. So given an image, you first smooth, average, and then averaging will blur the image a little bit, and then you find derivative. So that's kind of basic operation of edge detector, smoothing and differentiation. And then you apply a threshold to get an edges. So averaging can be like this. You can have, say 6 pixels or 9 pixel. You take the values, sum them up, divide by number of pixels here, and then derivative mask can be like this, the forward difference or backward difference, and you end up with something masked like that, which is combine the averaging and differentiation together. Okay, so this is in x direction, and you can have in y direction very similar, and these are the masks they came up with for the Prewitt edge detector. So when you want to apply Prewitt edge detector, you apply these masks. The first mask, which is shown here for the x derivative, and this for second derivative. I mean the y direction and this x direction. As you see, it is the same thing as I was explaining to you, that we are finding this central difference, but we are looking at the one row above and one row below to average it out. And this is the column-wise difference from the right column to the left column, find the difference. So that's the Prewitt edge detector. As I told you, that if you use a spatial in the MATLAB, it will do this, basically that. It will apply that to your image, give you the derivative image. So the Sobel edge detector is similar, very similar. The only difference is that the central row here has more weight. This has 2, and these have 1, 1. So it's kind of doing weighted averaging. The earlier one, all were same. Central one on the top, one on the bottom, were the same. So again, this is for x, this is for y, and you get a gradient magnitude by finding this thing, and then you get the like that. So if you take an image like that, apply the x mask, you get this image, y mask, this image, and then you can find the magnitude like that, and you can apply a threshold on that. Because if there's a derivative 0, which mostly you see black, dark, then there's no change, there's no edge. If the derivative is above some threshold, as you see here, these values, so these are the actual edges. Of course, there's some noise here, and there's a texture and some problem. But that's essentially is an edge detector. That you take the image, do little smoothing, compute the derivative, x and y, find the magnitude, apply threshold to magnitude, and you get edge image. So here, each pixel within the edge is black, the rest of pixels are white. So this is example of binary image, which means it's telling you that what pixel are edges are not edges. And this is the image actually color image, but we are only using one channel. It's a black and white image. So we find the derivative in x and y. So here we are not using anything color. But in principle, you can find the edges in red channel, edges in white, blue channel and green channel. Then maybe combine, but actually it doesn't help much. So it's fine to find edges in just one channel, gray level channel. Typical way to get the color image when you have 3 channels, you can just take RGB, R plus G plus B, divide by 3. So that gives you black and white gray level image. Okay? So, so that's that. And then we can talk about this edge detector, which is the Laplacian and Gaussian, as we have started already discussing. So let me give you a little background. So in computer vision, the research started from image processing and pattern recognition area. So image processing is the old area where the idea is you take an image and process it, and input is image, output is image. Okay. So mostly when you have pictures, people used to send for the newspaper, for some defense purposes and so on. So images have to be smooth, images have to be coded, like all the compression techniques, JPEG and so on. Or images have to be transmitted. You have to have a few number of pixels, or you can make it so that people cannot decode it. So all these operations are dealt with in image processing. There's a whole field. Actually, we have a separate few courses in image processing. But the main difference in image processing and computer vision is that image processing deals with the processing of images. It doesn't necessarily deal with analyzing images. So image processing field, input is an image, output is an image. In computer vision, input is an image and output is symbols. Say, well, there's a chair, there's a person, so that's the main difference. Even though that lot of operation in image processing are used in computer vision. Okay, so suppose removing noise and so on. So that's one field, image processing. The other field is pattern recognition, that you want to recognize patterns. You have some observations, and based on that you want to learn and you want to recognize that and so on. So computer vision came in from a field called artificial intelligence. So the idea there was that how can you build artificial systems using computers which are intelligent, and if you ask, vision is one of the intelligence humans have, that we can see, we can analyze things. Of course, we think about, we solve problems, we speech, and there are many different ways intelligence is defined. So then this thing started at MIT. There's a founder of artificial intelligence called Marvin Minsky. So he said, well, let's build artificial machine vision system, to basically, that was starting of computer vision. So he gave this problem as a summer project for 2-3 students, undergraduate students at MIT. So, but quickly they found out it is a hard problem. When you take pictures and you want to analyze, even those objects were, very simple objects like blocks. That's why there's a lot of work in blocks world, in AI and vision. So then people from image processing and from pattern recognition and a little bit from AI, so they started realizing that, the vision is a hard problem. Because at that time they were struggling with edges, to find edges. They say if we can find edges, we can fit lines, we can describe the planes, polyhedral objects and all this thing, we can reason and so on. But they were having problem to find edges because those time the cameras are pretty bad and very low resolution and so on. So most of the work which was done before that, was more ad hoc. So, well, I look at the image, I want to do that, so go through the image and find the difference, this thing. So there was not a mathematical foundation to that. Then there is this researcher called David Moore, who was British, neuroscientist. He came from England, went to MIT as a visitor, and he got interested in this AI and computer vision and so on. So, and he was very, very influential guy. And he said that first thing is that in order to solve vision problem, we need to look at the human vision, how humans are doing, how these cells, the research people have done, what are these operations and so on in the brain. So the first thing actually he did is came up with this edge detector with student Ellen Hildreth, who was a master's student at MIT. And so since they have done studies that while humans have these cells in the retina which are like Laplacian Gaussian, and they are detecting edges, so that's where they started. So now the Moore-Hildreth edge detector essentially have these operations. That first you want smooth an image, then by Gaussian, and then find the derivative. Now here they want to find derivative, the second derivative in x and second derivative in y. Now as we talk about, if you want to find the change, we look at the first derivative. Okay, so look at maximum and first derivative, that give you edges. That's what we applied the threshold, we got edges. Now if you want to look at the second derivative, if it is maximum and first derivative, second derivative will be 0. Okay, and third derivative will be negative. So that's what the idea they have said. Well, instead of looking at the gradient or first derivative, let's look at the second derivative and look at the 0 crossings. So since we're 2D, so second derivative x, second derivative y, add them up, that's called Laplacian, and look at the 0 crossing in there, and that's edge detector. Compared to what we talked about, Prewitt and Sobel, they say first derivative in x, first derivative y, find the gradient magnitude, apply a threshold to that. So there was two different things. And there, in Sobel and Prewitt, the smoothing was very simple. It was equal weighted. But here, the smoothing is by Gaussian. So those are the things came up with. And so this Laplacian operator is has a lot of applications, and so we find 0 crossings. So we look at the image, scan around x and y, and find the 0 crossings in the image. Okay, so I think we are going to stop here because we are close to the time, and we will then continue next week. Okay, thank you.